Hi and welcome to video 2 of the 4. In this video we're going to explore the relationship between the amount of reactant that you have for a particular process or reaction and how much heat is given off. And spoiler alert, the more stuff you react, the more heat you either give off or take in depending on how things go. Alright, so let's get going. So the group activity that I would have otherwise have had you do starts with these reactions right here. This is a reaction called thermite. Google it, take a look at it if you are so inclined. And it is the reaction of iron 3 oxide, good old-fashioned rust, with aluminum metal to form iron and aluminum oxide. I should note that so I have a picture of this reaction being done. That big ball of fire and sparks on the Learn page is this reaction right here. It's actually sufficiently, and you'll note that this gives off quite a bit of heat. Now the first question that I would ask you is what's different about these three reactions? Or what's new? And what you haven't seen before are these things right here. So this is a statement that tells you how much heat is given off for these processes. So delta H, remember, under constant pressure conditions, heat is a state function, and so we call it enthalpy, or H. Now, you can actually read this in this manner, that 1 mole of iron oxide reacts with 2 moles of aluminum to form 2 moles of iron and 1 mole of aluminum oxide. And in those proportions, this reaction will give off 851 kilojoules. If that seems like a lot, it is. And when you do this, initially, the iron and the aluminum oxide are actually liquid, and they don't, and they take a minute or two to cool down back into solids. So this is what makes it, this addition right here, this delta H tacked onto it, is what makes something a thermochemical reaction. All right, so the next set of questions I would have asked you on this group activity would be to look at these reactions again and ask you to assess the difference or the relationship between the amounts that are reacted and the heat that's given off, and how these reactions are related to each other and how these numbers are related to each other. So for example, what's the difference between reaction 1 and reaction 2? What do you do to reaction 1 to get reaction 2? And what's the relationship between the delta H for those? And likewise, compare reaction 1 and reaction 3. What's the relationship between these reactions, and what's the relationship between the heat that's given off? So hit pause, think about it for a sec, and come on back. Welcome back. All right, so you're supposed to describe the relationship between the change in the reaction and the delta H. So if you look at reaction 1 and reaction 2, you can imply that these coefficient change means that you're doubling how much reaction you're doing. So instead of reacting 1 mole of iron and 2 moles of aluminum, you're reacting 2 moles of iron and 4 moles of aluminum. Proportion is the same, the amounts are doubled. And hopefully you realize that, unsurprisingly, the heat given off actually doubles as well. This is a lot of heat. This reaction, if you look at the picture on the Learn page of that big ball of fire behind the blast shield, that's this reaction right here. And it gives off a lot of heat, enough so much that initially the iron and the aluminum oxide are actually melted. All right, so now let's compare reaction 1, reaction 3. What's the relationship between those two? Well, these are reversed. In this case, iron and aluminum oxide are the reactants. In reaction 3, they are the product. And what's the relationship between the delta H's? They too are reversed. So if you change the amount by some factor, the delta H is changed by that exact same factor, doubled, tripled, halved, whatever. And if you reverse the sign of a reaction, that is just simply reverses the sign of the delta H. All right, so this is an important skill to know. All right, so the changes in the reactions are the same as the changes in the sign of delta H. All right. So still looking at these three reactions, let me ask you, if you only had a mole of aluminum at your disposal and had plenty of iron oxide, how much heat would you expect to be released if you only had that 1 mole and not, let's say, the 2 that are indicated here? So take a second to think about that and come on back. All right. Hopefully you had some sort of reasoning that said, well, if I get if I release 851.8 kilojoules with 2 moles of aluminum, if I react half of that, I should get half as much, which clocks in at 425.9 kilojoules being released. And you would be completely correct. This is the essence of thermochemical stoichiometry. It is sufficiently easy that you pretty much probably got it in your head. And it is so easy that you probably don't realize exactly how you did it. So I'm going to point out that within these thermochemical equations are conversion factors. What this is telling you is that 2 moles of aluminum is equivalent to the release of 851 kilojoules of heat. Likewise, 1 mole of aluminum oxide is equivalent to the release of 851.8 kilojoules of heat. And with these equivalent statements, you can build conversion factors. And so this equivalency statement gives you the conversion factor between an amount of aluminum and a quantity of heat that is given off, in this case in kilojoules. And so starting point, you have 1 mole of aluminum. Conversion factors. For every 2 moles of aluminum, you get negative 859.8 kilojoules. That means the negative sign means it's released. And that gives you a total of negative 425.9. And so the rest of this activity, actually, you pretty much know. So if you can figure this out, the way that you normally see these problems is so there's really only one level of complexity that can get added to this. And that's a question that looks like this. Generally, you are relating a mass of a reactant or product to the amount of heat given off. So the next question in the activity was actually this. How much heat would you expect to be given off if you reacted 83.2 grams of iron, or if 83.2 grams of iron was formed? And so it doesn't matter whether something is a reactant or a product, you can still construct the equivalency statement and the conversion factor the same way. So the conversion factor here would be 2 moles of iron corresponds to negative 851.8 kilojoules. So the only thing that you need to add to this is the fact that you're given a mass of iron, and this relationship that you get from this to the thermochemical equation is in terms of moles. So you've got 83.2 grams of iron. You know that each mole of iron clocks in at 55.85 grams of iron. And you know from the equation that for every 2 moles of iron that you make, you will also release 851.8 kilojoules. So grams of iron cancel, moles of iron cancel. You're left with kilojoules. That's an amount of heat. That's good. And the numbers clock in at 634.5 kilojoules. All right. And again, you can also, the next question would have been to have you figure out, let's say you were inclined to produce 300 kilojoules of heat, how much aluminum would that take? And I think we'll go for a mass. So hit pause, work that out, come back. And hopefully, again, so starting point are 300 kilojoules. The equation tells you that for every 2 moles of aluminum, you will release 851.8 kilojoules. This would give you an amount of aluminum that you need. And you look up the molar mass of aluminum to convert that to a mass of aluminum, and that would require 19 grams. And That pretty much is thermochemical stoichiometry.